Good morning. My name is Hannah, and I am the social media manager at COSI. Thank you for joining me today for the 2021 COSI Science Festival. The festival has moved from a 4-day physical festival to an all-digital format May 5th through 8th. On May 8th, we hope you will connect virtually with at-home science activities and share your experience with photos or videos on social media using hashtag COSISciFest. And of course, we want to give a big shout out to all of the sponsors and partners of the COSI Science Festival, especially our visionary sponsor, Patel. We certainly couldn't do this without them. Want to show your support for COSI? We are nominated once again for USA Today's 10 Best Science Museum. You can vote for COSI by visiting cosi.org/10best. And don't forget, COSI opens to the public on June 3rd. Now, it's my pleasure to welcome you to today's event.
Hello, everyone. My name is Tawnya Laughinghouse, and I am manager for NASA's Technology Demonstration Missions Program. I am so thrilled to be with you today, and I really appreciate the COSI Columbus, Ohio Science Festival for inviting me and allowing me to share some really cool NASA space technology. So the Technology Demonstration Missions, or TDM for short as we call it, is the largest program under NASA's Space Technology Mission Directorate. And along with an amazing team, I manage our program from our program office at NASA Marshall Space Flight Center, which is located in Huntsville, Alabama. In my program, we take new technology and test it every way possible to make sure it works before giving it the thumbs up to be included on big missions to outer space. A lot of these technologies eventually may end up being used by you one day. So as we look forward to the current state of the art, what our program does is we look at the current state of the art to figure out what the future requires, what technologies will be needed, and how we can infuse and deliver those technologies to enable the mission needs of NASA and our government and commercial partners. So it really gives me tremendous satisfaction as TDM program manager, knowing I have a hand in making sure we have the cutting edge and new and innovative technology that enables rewarding new space missions that ultimately advance human exploration and our understanding of the solar system and the universe around us. The focus of my presentation today is our latest technology demo mission, which is about to be launched to space next month. We are so excited. It's the Laser Communications Relay Demonstration. Before we get to that, I'd like to tell you a little bit about our NASA TDM program and how technology drives exploration. So TDM manages and funds a really large and diverse group of technology projects with teams that are spread out all across the United States at different NASA centers and at our space industry partners. And what we do is we look at those technologies that they are managing. And since I've been with the program, we have launched about 5 different technology demonstration missions to space. A sample of which includes the Green Propellant Infusion mission, where we demonstrated the first ever non-toxic propellant fuel, which powered a spacecraft, and the Deep Space Atomic Clock mission, which is still orbiting right now, and is demonstrating how spacecraft can autonomously navigate, which means they navigate on their own without any guidance back at Earth. And technologies from DSAC will also be used to improve GPS technology, so that's also exciting. And then 2 of our technology demonstration missions, Terrain Relative Navigation and Mars Oxygen In Situ Resource Utilization Experiment, which is a mouthful, which is why we call it MOXIE for short, were both part of the history-making Mars 2020 Perseverance rover mission. That mission, as you know, has just been making history right and left since it landed. TRN enabled that successful landing. In fact, it was the most precise landing ever of a rover on the surface of Mars at the Jezero crater. And the MOXIE instrument, which is the size of a toaster oven, demonstrated a way that future explorers might produce oxygen from the resources already on the planet. Specifically, it was the Martian air, which is very rich in carbon dioxide. This little MOXIE instrument, about the size of a toaster oven, converted the carbon dioxide-rich Martian air into oxygen. And this is going to be critical for our astronauts in the future when we send our astronauts to Mars, not only to breathe, because we need oxygen to breathe, but we also need that oxygen to be produced to make propellant, to make rocket fuel, to send these astronauts back home when the mission is over. So it's been a really exciting past few weeks as MOXIE has successfully demonstrated that this can be done. And it's taking us one step closer to sending humans back to the moon and then on to Mars. So before I go any further, next chart, please. I'd like to introduce myself a little bit more fully, share a little bit of my background and how I ended up working this really cool job for NASA. My goal today, besides sharing NASA technology with you, is to help our budding scientists and engineers out there know that anything, and I mean absolutely anything, is possible with opportunity, with hard work, and the ability to imagine and see yourself one day in the STEM career that interests you. So here's an all about me chart. And for those of you in Columbus, Ohio, where your amazing cozy science festival is located, you might be wondering why I have a picture of the Ohio State Buckeye mascot on this page. Well, in fact, I was born in your hometown many moons ago. When I was a little girl, my family moved to Huntsville, Alabama, and that's where I attended school from kindergarten all the way up to high school. When I was in middle school, I thought I had my life plan all figured out. I wanted to become a doctor. I wanted to specifically become an obstetrician. I didn't think there was anything cooler than delivering babies. And that was the path I thought I was meant to be on until I was selected for a high school internship program at NASA Marshall. This program was called SHARP, or Summer High School Apprenticeship Research Program. And the picture on the bottom of this chart includes me and my fellow SHARP students in 1990. And each of us were matched with a mentor who was an engineer or scientist. I happened to be matched with a physicist for 8 weeks, and we worked on a special project. And in fact, the first project that I worked on at NASA was a project called Optical Data Collection Techniques and Analysis, which is absolutely amazing because as I look back and got prepared for this, I realized that all these years later, as a program manager, we're about to launch a program, a project on laser communications. And my very first project at NASA was working with lasers. I had no idea that it would have such an impact on my life years later. So please let that be a lesson to you, that doing your best early in school can have a huge impact on your success later in life. So that internship really changed my life because I began at that point to imagine myself working for NASA, and it really excited me. That summer, I learned about a college scholarship that NASA created in partnership with Spelman College called WISE, or Women in Science and Engineering. It seemed like the perfect vehicle for me to pursue my new STEM career interests, and so I applied. Well, I was selected, and I ended up majoring in chemistry at Spelman and chemical engineering at Georgia Tech, which are both in Atlanta, Georgia. After graduation, I worked in the manufacturing industry for a few years, went back to school to get my master's in management with a concentration in management of technology, which is another amazing connection because I manage a program that demonstrates technologies now. And I did this master's at the University of Alabama in Huntsville. After that, I was hired by NASA in 2004, and here I am today working what I consider to be a dream job. So in TDM, our team stays busy because we have so many technologies that when one or two have their day in the sun or get to have a big historic launch or prove out their demonstration or operate in space, we have another technology demonstration which is not far behind. And that's where we are today, with the upcoming June 2021 launch of the Laser Communication Relay Demonstration. Next chart, please. So over 50 years ago, Neil Armstrong and Buzz Aldrin took the first steps on the moon as part of NASA's Apollo 11 mission. Now, this happened, I'm not 50 yet, so this happened before I was born, but over 500 million people watched him, Neil Armstrong, walk on the moon. However, the footage that was sent to Earth capturing this incredible event, with the picture as you see on the top left, shows that it was a low resolution and really grainy image to viewers. Now, astronauts will soon journey back to the moon, as you see depicted on the right, this time with NASA's Artemis program. They intend to build a habitat there for longer stays on the moon, and will also be there to support future studies. So as you can imagine, we'll want to see every future step clearly and in high definition, especially when the first woman or the first person of color walk on the moon in the very near future. For that to happen, the instruments and technologies of the past will not cut it. We need new technology that supports our 21st century needs. We will need laser communications. With Lcrd, or Laser Communications Relay Demonstration, NASA is taking the next step to mature lasers or optical communications. And you'll hear laser and optical, that's essentially the same thing as I talk throughout my speech today. Next chart, please. So why laser communications? Well, since the dawn of space exploration, NASA has used radio frequency to send and receive information from satellites in space back to Earth. There is no doubt radio waves have a proven record of success. And with radio waves, as communication travels, the waves spread out, creating that grainy visual or scratchy audio, especially when traveling millions of miles from outer space. And there's infrared light or near infrared light that these lasers are sending back to space. And it's different because it actually packs the data into significantly tighter waves. So with radio waves, think of it as being a really broad beam. With laser communication, it's much tighter, which is why you see me closing up my fingers. Meaning, when we do this, we can receive more data at once. And as space missions generate and collect more data, the need for enhanced communications and capabilities is really important. So as a result, laser missions can send back 10 to 100 times more data than ever before, which means that if we can send and receive more data and more information, we can learn even more about living and working in space and in our solar system. And in the future, radio and laser communications will work hand in hand to support missions near and far. Next chart, please. So this next chart has a really cool animation video to show you how Lcrd works. So before we actually use it to support real missions in space, we'll want to test it out first. And Lcrd will demonstrate its capabilities between ground stations on the Earth. The Lcrd mission will operate for about 2 years. It will start off talking with ground stations, one in California and one in Hawaii, to test the invisible near-infrared lasers. Engineers will beam the data to and from the satellites, which are located more than 22,000 miles above the Earth, to refine the transmission process. They'll also be studying different operational scenarios and really try to perfect those tracking systems. And since we can't replicate those same conditions on the ground, this kind of information and data is really essential for readying these laser communication systems for an actual operational mission. Next chart, please. Now, this is a picture of our ground station. It's actually in Hawaii, which, as you can see, is like an optical telescope dome. Whenever I see it, I think of Cyclops. Maybe you do too. So during actual missions using laser communications, they will send their data to Lcrd while it's in space from a separate location in space. And then Lcrd will transmit that information down to one of the 2 ground stations. The one you see here is in Hawaii. And do you know why NASA chose California and Hawaii, and why those geographic locations might make laser communications easier? Well, if you said cloud coverage, you would be correct. These 2 locations were preferred due to the fact that they don't usually have many clouds. Cloud coverage can actually disrupt laser transmissions. However, we know because of weather, there will be clouds sometimes. So when they are, Lcrd has other workaround scenarios, gathering valuable information about the impact the clouds are having on the laser transmissions and the laser communications flexibility. Or if the cloud cover is extremely heavy at, say, the Hawaii ground station, Instead of causing a delay, LCRD can simply send the data to the other ground station, which is in Table Mountain, California. Next chart, please. So what are the benefits of using LCRD? Just how much data can we transmit at once with laser communications? Well, sending a high-resolution map of Mars back to Earth would take around 9 years with current radio systems on board spacecraft. But using laser communications, it would take as little as 9 weeks. So that is a huge difference. That speed, or more accurately, data rate, is really appealing for future human explorations and science missions. The systems also offer a smaller package. Laser communication systems can take up less space, less weight, and less power on a spacecraft, meaning a longer battery life, more room. That if it's less space, that means there's more room for you to have advanced instruments on the spacecraft. And then there's also some potential cost savings at the launch due to lighter payloads. Optical communications also provide significant benefits for missions, again, including data rate increases of 10 to 100 times more than comparable radio frequency communication systems. This increase means higher resolution data for the missions, giving scientists a much more detailed look at our planet and solar system. And then LCRD will also help NASA update how astronauts communicate to and from space. Later on in the mission, LCRD will conduct an optical communications relay with a future terminal. It's called Illuma-T, and it'll be on the International Space Station. This will happen around 2022 at the moment. And as NASA goes back to the moon, laser communications can empower sustainable communication architectures to help set us up for a human presence at Mars. Also, faster speeds, LCRD can communicate over infrared waves at data rates of 1.2 gigabytes per second. That's fast. This speed is faster than most Americans experience through our internet. And when astronauts are living and working on the moon, they will, of course, need reliable communications with mission control. And so this knowledge gained with LCRD will help NASA prepare for laser terminals going to the moon as part of the Artemis mission. And LCRD and its ground stations will demonstrate optical communications as a relay, which means missions will be able to transmit data from different points in their orbit without having a direct line of sight to the ground stations. So that is very key. Next chart, please. This next chart is a really cool poster on the left that I know my 11-year-old would want on his bedroom wall. This is the STP-3 mission, which is the actual mission our LCRD payload is a part of. LCRD is just one of many payloads on this mission, which will launch from Cape Canaveral in Florida. This mission is led by the United States Space Force, and the launch vehicle is an Atlas V, which is pictured on the right. And that's a picture of it being launched in 2011 for NASA's Juno mission, which sent a planetary probe to the planet Jupiter. So once in orbit, engineers located at LCRD's Mission Operations Center in Las Cruces, Mexico, will turn on the payload and will begin transmitting data between LCRD and the ground stations. LCRD will then spend the next 2 years testing laser functionality with various experiments, and that will include studying the atmospheric impacts, those clouds we were talking about, on the laser signals and demonstrating reliable relay service operations. Next chart, please. There's a picture of the payload being integrated on its space vehicle. So the picture on the right might not look very big, but the LCRD payload is actually the size of a king-size mattress. And that is only, as I said before, one of many payloads on the Space Force Stp Sat6, which is a satellite and space vehicle that was built to accommodate all of these payloads. And like many NASA missions, LCRD was a joint effort between government, industry, and academic partners, as you see on the left, to design and build the payload. Massachusetts Institute of Technology, Lincoln Laboratory, and Goddard Space Flight Center in Maryland are leading this effort. Again, this is a listing of all the NASA partners. And if you don't know anything else, know that everything NASA does is because of the amazing teams and partnerships that we have to enable us to make these amazing achievements. It is truly a team effort. Next chart, please. All right, here we see the entire Stp Sat6 satellite, which is a space vehicle, which includes Lcrd on the bottom. So watch as the video zooms in for a closer look at the optical modules. There you see them right there, which are actually telescopes that are used to send and receive those laser signals. Isn't that fascinating? All right, next chart, please. As you can see here, Lcrd is actually the second laser communications demonstration. At the very top left, you'll see that the Lunar laser communications demonstration was actually the first one launched in 2013. So Lcrd is actually a follow-on mission to that groundbreaking Lunar laser communications demonstration in 2013. After the success of that, NASA created this laser communications roadmap, which this is a chart of, that will help pave the way for future missions. There are currently several missions, as you can see on this chart, in development that they will help standardize and advance the speed of laser communication systems. At the top right, the Deep Space Optical Communications mission is another TDM optical comm mission, which will be hosted on NASA's Psyche mission and is scheduled for launch next year in 2022. So when you standardize technology, it eliminates the need of missions to kind of start from scratch and redesign the system from the ground up, which of course saves time, which is schedule, and money. And all of this work is fundamental to developing what we call LunaNet, which can be described as internet for outer space. Lcrd will enable this space internet to give our astronauts, our rovers, and orbiters a digital connection from space to ground. This evolution to a more internet-like communication will reduce the amount of processing that's currently needed and required before spacecraft can send data to science and mission operations centers from space. Next chart, please. So please make plans, mark your calendars, and join us for the Lcrd launch party on NASA TV. We are anticipating the launch window to open on June 23rd. That's only 7 weeks away. And though the U.S. Space Force, who's leading this mission, is expected to officially announce the date around the middle of this month. NASA's Lcrd will blast off to space and show the world the benefits of laser communications. Next chart, please. So this chart and the two after that are really some wonderful resources and websites for you to visit to get updates and learn more about the Lcrd mission, about optical and laser communication activities at NASA. You can take a shot of these links, but we'll also put the links in the chat. And next chart, please. I believe are some fun activities for the kids, and we think you might enjoy them as well. You can find this activity and others by Googling NASA Scan, that's SCAN, and Kid Zone. It should pop right up. On this page is a simple decoding activity to get a special message to the kids. On the website are versions for older students as well. And we also have coloring sheets available for the little ones. And on this next chart, it's another fun activity called Speaking in Phases. Earlier, I explained how spacecraft put actual information into the radio signals that they send back to Earth. In this activity, you will beat out the rhythms on drums or tables and send messages using the same principles used in space exploration. All the details and instructions are on the website. So this includes my presentation today about NASA Space Tech and our upcoming laser communications relay demonstration. Are there any questions for me? All right, let's see. I see a question. Is there a project you haven't had a chance to work on in your career that you would like to in the future? That is such a good, question. Huh. The James Webb Telescope, it's such a big effort for NASA, and it's something that I'd love to be a part of. As a matter of fact, I just love learning about it. And that is something that NASA Goddard is leading that one. And I have lots of colleagues around the agency who have contributed to it. And so that's certainly a huge a huge project that I haven't had a chance to be a part of. That would be interesting. Next question. As a kid, what did you want to be when you grew up? Well, I was saying as I started in middle school, I thought I wanted to be an OBGYN, an obstetrician gynecologist, deliver babies, and I thought that life would be set. But you know what? It's funny because even before I started the NASA internship, I was starting to kind of waffle a little bit on that. And I was thinking about my own parents and the fact that, mom and dad were always, worked hard, but were always at my events. And I started kind of thinking, well, if you become a baby doctor, as I called it at the time, you probably will have to deliver babies at all times of the day and the night. And it probably will take me away from my family a little bit more than I was comfortable with. And yes, I was precocious. I was thinking about these things even in middle school. But so I think it was fortuitous that I found out or was selected for this NASA internship program. And it really, it really changed my life and really got me thinking about a career in STEM. And then it didn't hurt that the hours, were a little bit more manageable. Let's see. Do you ever work with astronauts? I do not. It's so funny. When I was telling my mom that, I was excited and planning to work for NASA as a career, she would always, she'd be a little bit concerned about me. And she said, I hope that you don't decide to become an astronaut. And I told her, I said, it's so funny because I've always admired and I just don't think there's anything, much better than being an astronaut, being a trailblazer. But in my heart, that has never really been where I wanted to work and perform. I really wanted to help the astronauts get where they needed to go. And so when I first started NASA, I was in the materials and processes laboratory as a materials engineer. And I worked on the solid rocket boosters. And specifically, I was in charge of, I was the lead materials engineer for the booster separation motors, which are like these 31-inch long boosters. They're about 16 on the shuttle. And when they ignite, they actually separate those big solid rocket boosters as they fall back to the Earth. And, that happens, a little over 2 minutes into the launch. And that was what I wanted to do. I wanted to help and make sure those astronauts got there safely. And that was a part of my job earlier in my career. I've been with NASA about 17 years now. So the first 12 years of my being with NASA, I was in the materials and processes laboratory working for Shuttle and then the SLS or now Artemis program. And so I've just been very fortunate to have been working with making sure our boosters are the materials or what they need to be so that they can withstand all those high temperature conditions and to do their job so that there's a safe launch. So that's wonderful. Are there any women that any women in STEM that you look up to, past or present? Oh my goodness, there are so many. It's I tell you, when I became a NASA WISE Scholar, that was the partnership between NASA and Spelman College. It was an amazing program, and I was selected. Spelman is an all-female HBCU in Atlanta, Georgia, a private school. And there were students like me who were selected from all over the country. Many of them were from areas where there were NASA centers. And so the program was amazing. And one of the first programs that we had together, guess who came to talk to us? It was astronaut Mae Jemison. And so while I didn't get to work with her, I did get to meet her. And she came to talk to us about her career and to give us encouragement as we started this program, knowing that, we would be working to ensure the safety of her and her fellow astronauts and contributing to the mission of NASA. And so she was a huge influence on me starting off in this STEM journey, especially my STEM educational journey, and helping me to see what the end goal could be, what the end result could be. And of course, learning about the hidden figures at NASA through the book and the movie that came out. It was just amazing that I was really shocked that I didn't know about these amazing women before their story actually hit mainstream, and I was just floored and so amazed. And even though I've always had an amazing aptitude in science and math, I'll say amazing, but I was always a really strong student in science and math. But I think what the amazing thing about their story is how many little girls and little boys just would have been so inspired by knowing the stories of these women, Dorothy Vaughan, Mary Jackson, Katherine Johnson, knowing that they existed and the amazing role that they played at NASA in the early years, just knowing that they were there, how that could have inspired them to become whatever they wanted to be. So many times our little girls and sometimes little boys get discouraged in school and don't have anyone to look up to or don't know anyone who's in those roles or maybe in a STEM career, and they just don't feel encouraged. And I just think how many little girls and little boys could have really benefited from knowing those stories years ago. I'm so happy the stories are out now. And I also want to say that I had just some really exciting times in my career. I was actually at NASA headquarters in Washington, D.C. the day that they renamed the street in front of NASA headquarters from E Street to Hidden Figures. And so I've got a picture of myself standing under the Hidden Figures sign on the day that it was dedicated and renamed. And then, as you know, very recently, just a month or two ago, they renamed NASA headquarters in honor of Mary Jackson, who was the first African-American woman engineer, and she was from Langley. And so NASA to me has long recognized the need for ensuring that we have a pipeline of diverse talent. And because we know that it's through, diversity of thought, having people on teams that are from different backgrounds, different perspectives, that we all working together can really find the best solutions. It really doesn't happen when you are all thinking the same, all think about, and no one's really challenging you. That's not usually how you find the best decisions. And so I want you all to remember that, having the right people on the team. And that doesn't mean everybody who went to the same schools or maybe a school that's really important even in your area, even in Columbus. The Ohio State is prominent, but you don't want a team just full of everybody that's from the same place. You want some diversity, and it's through diversity that you arrive at the best conclusions. It's also important as a leader to make sure that everybody on your team has a voice, that you're not just listening to the people who speak up first, who raise their hand first. Even in class, you all may have classmates like that. Doesn't mean that that's always the right answer or the best answer. Sometimes people need a little bit more time to think a thought through, or to come with a good. So as a leader, you want to make sure that you are looking at everybody in the room. You're calling on those people who might even be in the back, who maybe think their idea is not that great until they voice it and everybody realizes, whoa, we never thought of that before. So, and I think having, more women, more underrepresented groups, different age groups, all of you working together to make sure that you help NASA and your own organization be successful, your own teams. All right. Let's see. Is there a specific challenge in your career that you have had to overcome, and how did you overcome it? It's really interesting. I tell students all the time, especially young students, young female students that I may talk to, that there was a time when people used to say, "Oh, I think women can have it all," and I think in some respects you can, but for me, it's not having it all at the same time. As you know, when I was talking about delivering babies and maybe wanting to be an obstetrician gynecologist, being there for my family was really important for me. And so as I came up through NASA, I was identified and kind of seen as someone who was, very proactive, kind of an emerging leader. And one of the things that I was presented with was an opportunity to go detail somewhere out of my hometown. And I had really young children at that time. And I decided I was really torn because I really wanted this opportunity, but I was actually at the very beginning of starting a family, and I really didn't want to, and I wanted to honor that and, really start that process. And kind of, look for more career, development and growth opportunities later. And I had a male manager, and most of my managers at NASA have been male into the last few years, but who told me and gave me the best advice that I will never forget. He said, "Tawnya, don't ever apologize for putting your family first. If these opportunities are coming around now, they will come again in the future. Don't ever, ever apologize for that." And that gave me a lot of peace. And I'm so thankful that I had him as my mentor and my guide and my manager at that time, because that's not always the advice that people could give, and especially to women coming up in this very challenging environment. And so I was able to politely decline that opportunity at that time. And a few years later, when I was ready to kind of start traveling and start doing some things again, those opportunities did come around. And I'm in a career and certainly in a position that I really love. So I don't ever want anyone to think that if you're a certain gender, there's certain things that you can't do because of commitments, of other commitments. Just realize you may be able to do those things. If you don't want to do those things now, you may want to, but if you don't want to do those things now, it's okay. And the type of leader that you are, the type of worker that you are, the fact that you get things done, those things, people want to grab onto that and they want you on their team. And so if you have, been working hard and you show that you have potential, those opportunities will come around again. And they certainly have for me at NASA. All right. And last question. If you could go back and give your younger self a piece of advice, what would it be? That's a really good question. I think a really good piece of advice that I would give myself is to give myself some grace. Not be so hard on myself at times. I had this innate drive to want to be my best, and it didn't come from my parents. I mean, they had high standards for us, but they didn't, they didn't push me and my brother and sister to do more than what they knew we could. They knew we had high potential. But I had this internal drive that didn't give myself a lot of forgiveness for messing up or something not working out right, or even failure. And so when so if I could look back and talk to myself then, I would tell myself that is how we grow. When we fail at something, that is an opportunity for us to learn from that failure, apply it to our lives, and do better. And I hope that all of you take that to heart, even those of you who might recognize yourself in me and realize that you're being too hard on yourself as well. And I think of so many people who might be interested in science and math and maybe see that first bad grade and think, oh, that's not for me, I got to get out of that. Please don't do that. Don't do that to yourself. Give yourself some grace to get back. I actually did not pass my first chemical engineering class. And it was humbling for me. It was very, very traumatic for me. I have to say that. I came home that semester, and it was the most difficult thing, because I've never failed at anything in my life. I've always been a top student. I would get into a zone, and during a test, it was almost like I would freeze up. I could work on the homework assignments, great, and then I would get to a test and absolutely freeze up. And when I came home that semester, in tears, I think I drove home in tears the whole time. And I talked to my parents, and they said, okay, get the tears out. Now, remember, the Lord did not bring you this far to leave you. Just pull up and remember that you can do this. You have to believe you can do this, and you have to push through any fear, any feeling of maybe I don't belong. You have to push through that. And I did that. And I went back the next semester, retook that same class, and made an A. And I have not looked back since. So I want you all to remember that. I think that's all for me. Hannah?
Yeah, thank you for joining us today, Tawnya. We really enjoyed having you, and we will go ahead and wrap up now. Thank you so much.
Thank you.
Bye-bye.
Bye-bye.